Hi everyone, I'm Chan. I'm happy to be here today to be able to share the results for my alternative assessment for the subject High Performance Data Processing taught by Dr. Liza. So before I start my presentation, I would like to mention that all of the code I developed for this assessment can be found in my GitHub, which is accessible from the link over here. So let's get started. Alright, so in my presentation, I'll cover 3 topics, which are source code anatomy, where I explain the function of my source code and how I detect the rectangles. On the second topic is parallel implementation, where I show that how I implemented OpenMP and MPI functions to implement the parallel model. Alright, so the third is the performance analysis, where I show the analysis for my program to determine is it scalable or is it high performance enough. Alright, so let's start with rectangle detection logic. On the left, we have a flowchart, but I will not explain with a flowchart. I will explain in a more interactive way. So let's take an example of here that we have a 6 by 5 binary matrix with a rectangle of 1 in the middle. So the program starts to read line by line from the file. So let's read from the first line. So the program will determine whether there's a 1 in this line. So in this case, there's no 1, so we move on to the next line. Alright, so for the second line, the program determines there's a 1 in this line. So if that is the case, we will copy the line into the current line variable, which is a string variable, to hold the record of this line, and we will also record the row number of this line. Subsequently, we will carry out the walk line function to determine the top left coordinates and the top right coordinates of the rectangle. So if we are reading from 0 into 1, which means that we encounter the top left of the rectangle. And if we are reading from 1 into 0, which means that we actually reach the top right of the rectangle. We proceed to read the next line. So what we do over here is we compare the current line we read from the file and the current line variable we read, which is actually the previous line. Alright, so if the string is the same, then we move on to the next line because it's the same. Alright, so we proceed to the next line. So the next line is actually also the same, so we move on to the next line. And the last line is obviously different, so the string compare will return a different result. So that if the string is different, that means the chunk already ended in the previous line. So we can say that since the current row is 5, so the chunk actually ended in row 4. So the bottom right x is actually the same as the top right, which is 5, and the bottom right y will be the last row of chunk, which is 4. So we can conclude that the top left of the rectangle is 2, 2, and the bottom right of the rectangle is 5, 4. Alright, so you can see that our program actually can detect the rectangle successfully, and the highlights of this implementation is that we detect the rectangles when we are reading the file, and we only store one row of the string in our memory and not all. So it's efficient for memory. So that is how I implemented rectangle detection in my source code. So right now I would like to take a dive in my code. We'll take a look at the actual source code, and just a reminder, you can find this code in the link in below. So let's go. Okay, right now we're on subline, so we'll take a closer look at the rectangle detection implementation logic, which resides in the function read file. So I'll explain along with my flowchart. So as long as we are not reading enough lines, we keep on reading lines from the files. Alright, so this current string y is the row number of the non-empty lines. So if we do not encounter any non-empty lines before, this will have a value of -1. So it will enter this if block. Okay, so we'll evaluate, we'll check is there any 1 in this line by using a got1 function. So let's take a look at the got1 function. Alright, so what we do is we will traverse the line until we read 1 or we reach the end of the line. So if we read 1 before we reach the end of the line, we'll return 1, else we'll return -1. Alright, so this will indicate that is there a 1. Alright, so if there is a 1 in this line, we will run this code, which is actually copy the current line into the current string, and then we will assign the current row number into the current string y variable, and then we'll reset the top left and top right buffer, which will hold the coordinates of the top left and top right coordinates of the rectangle, and then we will walk the line. Okay, so the walk line is actually a simple function that reads the line. So if it is reading from 0 into 1, it will register the index into the variable into left hx variable, which will hold the coordinates of the x of the top left, and then the top right will be when we are reading from 0 into 1. So it will return the values in these two array. So that's it, and then we will keep on reading the lines. So right now we already have a non-empty lines, so it will not enter this block, instead it will enter this block. So what it does is it will compare the string that it read from the buffer, from the file, and then compares with the current string, which is the actually is the previous non-empty line. Okay, so it will evaluate. So if it is different, meaning that the chunk already ended, just like I explained just now, and then for this part is actually computing the rectangle's coordinates. So it will make sense to you very soon later on, because it is actually sending back the coordinates to the master thread. Alright, so this part over here is actually handling the current line. Okay, so because we are not handling the current line in here, but we should also check is there any one in this current line. So this method, this procedure will will continue to run until we read enough line, and at the end, because there's a possibility there where the last row is still have one, so we have to handle the very last row also. So as soon as that ends, the rectangle detection is complete. So over here is actually another parallel implementation. So we will send an empty payload, which I will explain in the next session very soon. So right now let's back to the slides. Next, let us move on to the next topic, which is parallel implementation. So we'll talk about master and slave model, decomposition strategy, and OpenMP and MPI implementation methods, and MPI communication methods. Alright, so without further ado, what is master and slave model? Master and slave model is a parallel model where we have a master process to break problems into smaller sub-problems, and slave process will solve these sub-problems and eventually return the results of the sub-problem back to the master, so that the master can combine the result into something useful, like printing the rectangles, combining the rectangles, and etc. So what decomposition strategy we use? We use domain decomposition in the source code, where we will break the bigger file into smaller chunks to process. So let me explain with an example. So I will explain the example. Let's assume we are running the program with 6 processors. So the number of slave process will be 6 minus 1, because we have one master process. So 6 minus 1 will be 5. So the number of each slave process have to read is 10,000 divided by 5, which means it's 2,000 lines. So you can see that actually each slave need to only read 2,000 lines compared to originally is 10,000 rows. So it will be much faster. So how do we actually break the file into smaller chunks? So the master process will compute the entry point for each slave process and then tell them the number of lines required to read. So different slave process enter the reading file at a different position. So there will eventually, when all slaves read all files, the whole file has been read. Okay, so before we take a look at the source code, so let me take a look at a multi-process, MPI multi-process. So as a summary, the master will determine the entry point and number of lines required to read by each process and allocate these tasks to these slaves. And master process will record the results returned from the slave process and eventually combine them and print to console. Whereby slave will initialize local variable the entry point and number of lines required to read that is being allocated by the master process, and read the file accordingly and perform the rectangle detection and return the results to master process. Alright, so let's take a look in the code itself. So in the main function, we have the master process to determine how many lines the slave process need to read and what is the entry point. So this is the part where the master process determine how many lines and what point to enter for each slave. Okay, so the data is being stored in this read quantity and starting line array. And in the main task, the master thread always actively listening, waiting for the slave process to return the results, whereby the slave process will perform the read file rectangle detection function. Alright, okay, let's get back. Okay, so for OpenMP multithreads computation, as you can see on the right hand side, the screenshot, we have my machine has 8 CPU cores, but each core have 2 hardware threads. So to take advantage of this hardware resource, we will use OpenMP parallel 4 to take advantage of using the maximum number of threads in each CPU process. Okay, so this is very useful when we are traversing very large for loop, as you can see in here. We are traversing very large for loop. So what it does, OpenMP parallel 4 will break the for loop and be processed by different number of threads in parallel, and combines it when they finish processing it, all handled automatically by OpenMP. Alright, so move on to MPI communication. The type of communication that is being used in this source code is collective communication and point-to-point communication, and actually total of 4 communication functions is being implemented, which is scatter, barrier, send, and receive. Okay, so before I hop into the source code, let me just explain with this diagram. So the master process, as mentioned just now, it will compute the entry points and the number of lines required to read. So the master process will use MPI scatter to scatter this data to each slaves. But before that, we use MPI barrier to make sure all slave has been ready, has been synchronized at the same point before dispatching to run a rectangle detection function. So when they have found rectangles, we will use the point-to-point communication MPI send to send the result back to the master process, which is by using the MPI receive function. So let's take a look in our source code. Okay, so the waiting part is over here, the MPI receive. Okay, so how about the read file? So the part that just now when we initially are discussing that seems doesn't make sense is actually here is the MPI send. So it will make sense to you right now because when the slave process detect a rectangle, it will send these coordinates back to the master. Okay, send back to the master, and then the master, when receiving it, it will store the coordinates into the buffer array, and then the master process will store the buffer data back to the identified TL, which represent top left X and top left Y, and accordingly bottom right and bottom right X and Y array. Okay, so this process is only done when all the slave process send the empty payload, which indicates slave process already finished executing. So in here, we will do a sum test to add up all the value of the buffer X. So if it is equal to 0, slave done will increment by 1. So if the slave done is equal to number of slave, meaning that all slave has already sent empty payload, we will stop receiving data. We'll stop receiving data from slave processes. Okay, so this is a complete flowchart of the parallel program. You can see that over here. Actually, master thread and slave threads are carried out in parallel, and this part actually is the same rectangle detection we discussed earlier. Okay, so just one thing to mention is at the end of the implementation of the rectangle detection, we will send the empty payload. The slave will send the empty payload to masters. Okay, so the master is actively waiting. So once the number of empty payload received equals to the number of slave, okay, so the master will combine the rectangles and then print the rectangles to the console. Okay, so and that marks the end of the program. Okay, so let us execute the program. Okay, as mentioned just now, I will execute the program with 6 processes. Okay, so the master thread will distribute the entry point and read and the number of line required to be read by slaves, and the slave when printing this line, this line is being printed from a slave process. So when we see this line being printed, we can make sure that the slave process already received their entry point and the number of line required to read accordingly. So they are reporting back to the console. So this is the rectangle that we detected. So there are total of 4, and we can measure the time being used. So this is useful for our performance analysis very soon. Alright, so now let's go back to the slides. Move on to the last topic of the presentation, performance analysis. We want to test the program, is it scalable or is it high performance? Alright, so to do that, I wrote a benchmarking script in Python which will run the program with different number of processes. So from 2 to 19, and each process will run 5 times. So I will take the average speed of the 5 trials and get the average number of speed. So right now, let me run the benchmarking script. Alright, right now the results are in. We can take a look at the benchmark output. We can see that with the increase of number of processes, the average elapsed time actually decreases. So which means that performance gain is actually significant. So from 4 seconds, 4.8 is around 5 already. From 4.8 seconds to 1.68 seconds. So we can actually say that our program is actually high performance and scalable. Okay, so with using the formula of performance index equals to reciprocal of execution time, we can plot this graph, okay, and we can see that with the increase of number of processes, the performance index also increases. Okay, so as my machine only have 8 cores, so after beyond this point, the performance index become unpredictable. Okay, so sometimes it goes up and go down, but generally it is decreasing because we are oversubscribing the MPI program. So that's all from me. So I hope that I share something useful for everyone, and thank you very much for your attention.